The universe appears random, but 26 celestial coincidences challenge that very idea. By the end of this journey, you will see the cosmos through a new lens, one where chance may not be the only force at work. We will uncover why the moon fits the sun so perfectly in an eclipse, and what ancient resonances among Jupiter's moons reveal about our solar system's design. These are not just quirks, they are profound mysteries that current science cannot fully explain. What does it suggest about our reality when the stars align with such impossible precision? For thousands of years, human eyes have turned upward, searching for meaning in the patterns of the stars. Ancient cultures like the Mayans and Egyptians built entire calendars and monuments around the sky, achieving a level of accuracy that still baffles us today. They could predict eclipses and track the wanderings of planets, yet they saw these events not as cold mechanics, but as the work of gods. The Saros cycle, a repeating pattern of eclipses every 18 years, was known to them. They saw its clockwork return, but the underlying reason for such a perfect, recurring alignment remained a divine mystery. Centuries later, scientific giants like Johannes Kepler and Isaac Newton gave us the laws of gravity and motion, framing the cosmos as a grand, predictable machine. Their equations could chart the paths of planets with remarkable precision, yet even their powerful models encountered stubborn anomalies, peculiarities in the orbits of distant moons that did not fit neatly into their calculations. This long history of observation, from ancient wonder to classical physics, reveals a persistent thread. We have always been surrounded by cosmic quirks that seem too perfect, too finely tuned, to be mere accidents of chaos. This enduring puzzle is the very foundation of our list, and it leads us directly to the first and perhaps most famous coincidence of all. This first coincidence is written in the sky for anyone to see. During a total solar eclipse, the moon slides perfectly over the sun. It is a spectacle of impossible geometry, where our nearby moon appears to be the exact same size as our distant star, allowing its delicate corona to blaze into view. This perfect fit exists for one simple yet staggering reason. The sun's diameter is roughly 400 times larger than the moon's, and by a twist of fate, the sun is also almost exactly 400 times farther away. This precise ratio is what makes the alignment so flawless. The odds of such a neat numerical balance emerging from the chaotic process of planetary formation are astronomically low. A slightly different moon, a slightly altered Earth orbit, and this perfect match would vanish. We would never witness the sun's magnificent crown. Scientists acknowledge this as a statistical marvel. Some call it a temporary gift, a coincidence of our current epoch, as the moon slowly drifts away from Earth over millions of years. Yet the timing of our existence, right in this narrow window where such perfection occurs, feels itself like a profound kind of luck. This perfect celestial alignment does not stand alone. It points toward a solar system where the planets themselves seem to be arranged by a hidden design, locking into resonant patterns that defy simple explanation. That same sense of a hidden design echoes in the very architecture of our solar system. 2 centuries after Newton, astronomers noticed something peculiar about the planets. They do not orbit the sun at random distances. Instead, they follow a strange and simple mathematical rule, a pattern now known as the Titius-Bode Law. This rule predicted that a planet should exist between Mars and Jupiter, a gap that was later filled by the discovery of the asteroid series. It also accurately foretold the orbit of Uranus before the planet was ever seen through a telescope. The pattern itself is surprisingly straightforward. If you take a simple sequence of numbers, you find that each planet's average distance from the Sun is roughly twice that of the one before it. This creates a kind of harmonic spacing, a cosmic rhythm that seems far too orderly to have emerged from the violent, chaotic cloud of gas and dust that birthed our solar system. Our best modern model, called the Nebula Hypothesis, explains how planets form from a spinning disk of material, but it struggles to account for this specific, neat doubling of distances. The gravitational interactions within such a disk should, in theory, lead to a much more random and messy arrangement. The great science communicator Carl Sagan called it a curious coincidence, a phrase that hints at a deeper mystery. This pattern is a genuine puzzle, a whisper of an underlying rulebook for building solar systems that we have not yet fully read. It challenges the very assumption that our cosmic neighborhood was assembled by chance alone, suggesting instead that some unseen principle guided the planets into their harmonious orbits. And just as we ponder this large-scale architecture, we find an equally baffling resonance in the motion of worlds much closer to home. This celestial harmony is not confined to the planets alone. Around the giant world of Jupiter, a dance of breathtaking precision unfolds. Its 4 largest moons, discovered by Galileo centuries ago, move in a gravitational lockstep so perfect it seems mathematically composed. For every single orbit completed by the largest moon, Ganymede, the moon Europa completes exactly 2 orbits, and the fiery moon Io completes exactly 4. This is a 1 to 2 to 4 resonance, a rhythm that keeps their paths stable and predictable across the eons. Think of it like 3 runners on a circular track, forever maintaining their positions, their footsteps timed so perfectly that they never collide. The odds of such a complex, multi-world synchronization emerging naturally are vanishingly small. Our most advanced computer simulations, which model the chaotic early solar system, struggle to recreate it. They often end with moons crashing into each other or being flung from their orbits entirely. While scientists point to tidal forces, the gentle gravitational tug of war between a planet and its moons, as a possible tuning mechanism, the exact sequence of events that led to this perfect configuration remains deeply elusive. It feels less like a random outcome and more like a piece of celestial choreography, a symphony written into the very fabric of our solar system. This profound order among Jupiter's moons forces a humbling question. If such intricate harmony can exist around a distant gas giant, what does that suggest about our own world's position in the cosmos? This stable, life-giving orbit is itself a profound cosmic coincidence. Our planet resides in what astronomers call the Goldilocks Zone, a narrow band around the Sun where temperatures are just right for liquid water to exist. Not too hot, not too cold. This perfect positioning is only the beginning of the mystery. Earth's distance from the Sun is precisely calibrated, but it is the combination with our protective atmosphere and a powerful magnetic field that creates an environment of remarkable stability. This balance has been maintained for billions of years through asteroid impacts and shifting climates, allowing life to not just emerge but to thrive and evolve. When scientists run models of how planets form, they find that such zones are typically narrow and often unstable. Worlds can easily veer into runaway greenhouse effects like Venus or freeze into barren ice balls. The fact that Earth has maintained this delicate equilibrium for so long is a statistical marvel. Astrobiologists like David Grinspoon point out that this fine-tuning might be exceptionally rare in the universe. It suggests we are not looking at a single lucky break, but at a series of fortunate events. This coincidence challenges the very foundation of theories about how common habitable worlds might be. If a stable, life-nurturing environment is this difficult to achieve and maintain, then our pale blue dot becomes even more special. It forces us to look closer at the other unique factors that make our world a sanctuary in the vast cosmic dark, and to wonder if our moon, so perfect in eclipse, plays a deeper role in this planetary stability. Our planet's graceful lean is another piece of this cosmic puzzle. Earth does not spin upright like a top. It is tilted on its axis by about 23.5 degrees. This specific angle is the sole reason we experience the predictable rhythm of the seasons. Without it, our world would be a far more monotonous and likely less hospitable place. Contrast this with Uranus, which is practically rolling around the Sun on its side with a 98-degree tilt, leading to decades-long seasons of extreme darkness and light. Or consider Mars, whose tilt can chaotically wobble over millions of years, dramatically shifting its climate. Earth's tilt, however, has remained remarkably steady. It does have a slight wobble, a slow circular motion called precession that completes a cycle every 26,000 years. Ancient astronomers, like the Greeks who discovered this precession, mapped its slow turn across the heavens. Yet the fact that the tilt itself has not wildly fluctuated is what truly baffles scientists. The gravitational tug from our giant planetary neighbors, especially Jupiter, should have, over billions of years, pulled and twisted Earth's orientation into chaos. Our models show that a planet's axial tilt in a multi-world system like ours is inherently unstable. So why has ours held firm? It is as if some unseen gyroscope is at work, a stabilizing influence that has maintained this perfect, life-nurturing angle through eons of cosmic turbulence. This persistent stability allowed for the dawn of agriculture and the rise of civilizations, all built upon a predictable climate. It is a coincidence of timing and balance that feels less like luck and more like a carefully maintained setting. And many researchers point to a single, massive object in our sky as the most likely source of that stability, our own moon. That stabilizing influence has a name, and it is our moon. Its gravitational pull acts as a cosmic anchor, a steady hand that keeps our planet's tilt from wandering into chaos. Without this lunar guide, Earth's rotation would become erratic. Its axis, wobbling wildly over time, spans as short as a few thousand years. Picture a spinning top as it begins to slow, its gentle wobble escalating into a violent, unpredictable shudder. That is what our world would be like, a planet of extreme and random climate shifts. One era could see the tropics freeze, while another turns the poles temperate, all within a geological blink of an eye. Such violent transitions would make the long, stable environments necessary for complex life, like forests and coral reefs, nearly impossible to establish. Our large moon is the exception, not the rule. Most other planets in our solar system do not have such a substantial companion. Mars, with its two tiny, asteroid-like moons, experiences dramatic shifts in its axial tilt over millions of years. Computer simulations of planetary formation consistently show that a moon as large as ours relative to its planet is a rare occurrence. Its very existence is tied to a cataclysmic and improbable event, a glancing blow from a Mars-sized object in the early solar system that splashed molten rock into orbit, material which later coalesced into our moon. This giant impact theory, while our best explanation, describes a cosmic accident of precise and unlikely proportions. As astrophysicist Neil deGrasse Tyson often highlights, this lunar influence is not a minor detail. It is a cornerstone of our planet's ability to nurture life. The coincidence lies in the chain of events, a perfect collision that gave us a perfect stabilizer. It compels us to ask if life-bearing worlds are almost always paired with such a celestial guardian, another thread in the growing tapestry of fine-tuning. And just as our moon locks our world in a steady rhythm, a different kind of orbital lock governs the sweltering planet closest to the sun. Far out in the frigid darkness, a cosmic dance defies all expectations. Even after Pluto's reclassification as a dwarf planet, it maintains a perfect gravitational lockstep with the giant Neptune. For every 3 orbits Neptune makes around the Sun, Pluto completes exactly 2. This 3-to-2 resonance is a stable, repeating pattern that has persisted for millions of years, ensuring the two worlds never come close enough to collide, despite their paths crossing in a way that would otherwise seem destined for disaster. The sheer improbability of this relationship is staggering. Neptune is a behemoth, its mass thousands of times greater than tiny, icy Pluto. According to our standard gravitational models, such a profound and lasting connection should be easily broken. The gentle tugs from other planets, or even from other objects in the Kuiper belt where Pluto resides, should have disrupted this delicate balance long ago. Alan Stern, the principal investigator for the New Horizons mission that gave us our first close look at Pluto, has pointed out that this dynamic is exceptionally rare. He suggests it may be a fossil from the solar system's violent infancy, a clue pointing to forces and conditions we have not yet accounted for. How could such a small body have fallen into and stubbornly maintained this perfect rhythm with a giant? This coincidence challenges the very foundations of orbital mechanics, forcing us to consider if these resonant harmonies are not rare exceptions, but fundamental features of cosmic architecture. Their mysterious origins compel us to look beyond individual planetary pairs to the grandest motion of all, the solar system's journey through the galaxy itself. Our journey through the solar system is not a simple circle. The entire planetary family, with the Sun at its heart, travels a vast, oscillating path around the galactic center. We do not stay neatly within the Milky Way's bright disk, but instead bob up and down through it like a carousel horse on a gently rolling track. This vertical motion has a rhythm, a cycle that takes us above and then below the galactic plane roughly every 30 to 40 million years. For a long time, this was seen as just an interesting orbital fact, a harmless feature of our galactic voyage. Then, paleontologists made a chilling discovery. The fossil record on Earth shows a startling pattern, a pulse of mass extinction events that appears to match this same 30 to 40 million year timetable. The timing is too close to ignore. As our solar system passes through the densest part of the galactic plane, a region thick with gas, dust, and gravitational disturbances, it is theorized that a cosmic shower is triggered. The gentle gravitational pull of the galaxy, a force called the galactic tide, tugs at the distant cloud of icy bodies known as the Oort cloud. This tug is thought to dislodge countless comets, sending them on a long fall inward toward the Sun, a journey that dramatically increases the chances of a catastrophic impact with Earth. The problem is that our models of this process are messy. The galactic tide is a weak force, and predicting exactly how it translates into a regular pulse of death from the sky has proven incredibly difficult. Some theorists, like physicist Lisa Randall, have proposed a more exotic culprit, dense disks of dark matter that could exert a stronger gravitational pull as we pass through them. Yet evidence for this remains elusive. This leaves us with a profound and unsettling coincidence. The rhythm of life and death on our planet may be conducted by a metronome whose beat comes from the far reaches of the galaxy itself. It suggests that our fate is intertwined with the grandest structures of the cosmos, a connection that challenges our understanding of where local events end and galactic influences begin. This blurring of scales forces us to look even deeper, to question the fundamental nature of the space and time through which we are moving. This delicate balance of life and death, governed by our galactic journey, pales in comparison to the most fundamental fine-tuning of all. The very fabric of space itself is stretched by a mysterious force, an energy inherent to the vacuum we once thought was empty. This is the cosmological constant, the number that dictates the rate of the universe's expansion. Its value is so precisely calibrated it defies all logic. If this constant were even slightly stronger, the repulsive force would have been so powerful in the universe's first moments that galaxies, stars, and planets could never have coalesced. All matter would have been flung apart into a thin, ever-cooling mist. Conversely, if the constant were just a tiny bit weaker, the inward pull of gravity would have overwhelmed everything. The entire cosmos would have collapsed back in on itself in a catastrophic reversal, a big crunch long before life could ever emerge. We exist in the narrowest of margins between these two extremes. Physicists have calculated that for a universe to be life-permitting, the cosmological constant must be fine-tuned to within 1 part in 10 to the power of 120. That is a 1 followed by 120 zeros, a number so vastly immense it is greater than the total number of elementary particles estimated to exist in the entire observable universe. Stephen Hawking called this perhaps the most startling number in all of physics. Our best theoretical framework, quantum field theory, predicts a value for this constant that is astronomically larger than what we observe, off by those same 120 orders of magnitude. The fact that the real value is not just small but perfectly positioned for our existence is a coincidence that shakes the foundations of science. This staggering precision forces cosmologists to consider radical ideas. Some propose the anthropic principle, suggesting that the constant has the value it does because we are here to observe it. In this view, our universe might be just one bubble in a vast multiverse, a cosmic landscape where every possible constant is realized, and we simply find ourselves in one of the rare habitable ones. Others see it as a sign that our theories are profoundly incomplete, missing a deeper principle that naturally leads to this delicate balance. This single number, governing the fate of all things, points toward a cosmos that is not just randomly assembled, but curiously arranged for complexity. And just as we confront the fine-tuning of the universe's expansion, we must turn our attention to an equally precise ratio that governs the forces binding it all together. This delicate balance extends to the very forces that sculpt reality. The strength of gravity, the power of electromagnetism, and the nuclear forces that bind atoms are not arbitrary numbers. They are set with a precision that feels almost intentional, a set of dials calibrated to allow for the existence of everything we know. The strong nuclear force is the glue that holds atomic nuclei together against the tremendous repulsive force of their positively charged protons. If this force were just a few percent weaker, that glue would fail. Atomic nuclei could never form, leaving the universe with only a featureless sea of hydrogen. No stars, no planets, no chemistry beyond the simplest element. Conversely, if the strong force were slightly stronger, it would overcome all barriers, causing protons to fuse together far too easily. The universe would have burned through its nuclear fuel in a frantic, short-lived burst, leaving no time for the slow, patient evolution of life. This is not the only critical ratio. The force of electromagnetism is perfectly balanced against gravity. If gravity were significantly stronger, stars would burn hotter and faster, exhausting their fuel in mere millions of years instead of the billions that allowed our solar system to form. Life would never get a chance to begin. Renowned astrophysicist Martin Rees has meticulously detailed these fine-tuned constants, arguing that their values appear to be a prerequisite for a complex, life-permitting cosmos. The staggering implication is that the fundamental laws of physics themselves seem rigged in our favor. Standard particle physics offers no explanation for why these numbers have the exact values they do. They are simply inputs to our theories, brute facts of nature. The multiverse idea that our universe is one of countless others, each with different physical laws, attempts to explain this by suggesting we naturally find ourselves in a universe where the numbers work. Yet this itself is a staggering proposition, one that replaces a puzzle of fine-tuning with a cosmic lottery of infinite proportions. This coincidence defies every expectation of random chance, forcing us to confront a universe whose basic operating principles are curiously and profoundly hospitable. This uniform glow from the dawn of time presents one of cosmology's greatest puzzles. The cosmic microwave background is the faded heat signature of the Big Bang, a snapshot of the infant universe when it was just 380,000 years old. When we map this radiation across the entire sky, its temperature is the same everywhere with staggering precision, down to variations of just 1 part in 100,000. This tells us the early cosmos was incredibly smooth, a homogeneous soup of matter and energy. Yet this very smoothness creates a profound logical problem, known to scientists as the horizon problem. In the standard Big Bang model, there simply was not enough time for heat to flow from one side of the universe to the other. The cosmos expanded too quickly for these distant regions to ever communicate and equalize their temperature. It is as if you had 2 cups of coffee, one in London and another in Tokyo, that somehow cooled to the exact same temperature without ever being connected. How could regions that were never in causal contact, that never touched or exchanged information, know to be identical? To resolve this, physicist Alan Guth proposed the theory of inflation, a moment of faster-than-light expansion in the universe's first fraction of a second. This sudden, colossal stretching would have smoothed out any initial wrinkles, creating the uniformity we see. The problem is that while inflation is a compelling idea, the exact mechanism that triggered it and then shut it off remains completely unverified. We have no direct proof of the inflaton field, the hypothetical energy driver behind this event. This leaves the profound uniformity of the cosmic background feeling like a monumental coincidence, a feature of our universe that our best theories can only explain by invoking an unseen, unproven process. It suggests the initial conditions of our cosmos were set with a level of precision we can scarcely comprehend, a fine-tuning that established the stage for everything that followed. Just as this ancient radiation reveals a universe set with impossible balance, a similar, protective form of fine-tuning operates much closer to home, within the invisible shields that guard our own world and its neighbors. Our planet possesses a powerful, invisible shield, generated by the churning of molten iron in its core. Earth's magnetic field extends far out into space, deflecting a constant barrage of lethal radiation from the sun. Without this protective bubble, our atmosphere would be slowly stripped away, and the surface would be bathed in levels of radiation that would make complex life impossible. This magnetic shield is unusually robust, especially when compared to our rocky neighbors. Mars, for instance, has only a patchy, weak remnant of a field, leaving it a barren and irradiated desert. The coincidence lies in its persistence. Planetary formation models indicate that such dynamos, driven by a liquid metal core, can and do falter over time. They can slow down, stutter, and even shut off completely. Yet Earth's magnetic field has remained strong and stable for billions of years, a timescale that perfectly overlaps with the entire history of life on our world. Geologists understand the mechanics. The field is sustained by convection currents within the outer core, a process that requires a perfect balance of heat loss from the core and the spinning rotation of the planet itself. But why has this delicate engine continued to run so efficiently in Earth's core, while it faded so long ago on Mars or never properly started on Venus? The answer may lie in a web of interconnected systems. Our active plate tectonics, for example, help regulate the planet's internal temperature, which in turn fuels the core's dynamo. Some researchers even suggest the Moon's gravitational pull provides a subtle, constant stirring of the core, acting like a spoon that keeps the pot from boiling over. This is not a single lucky break, but a cascade of them, where geology, orbital dynamics, and planetary chemistry align to create a durable sanctuary. It forces a profound question as we search the cosmos. Is a strong, long-lasting magnetic field just another line on the checklist for a habitable world, another piece of fine-tuning that must align? This intricate interplay of forces protecting our world finds a strange parallel in the silent, empty spaces that define our solar system's architecture. These pockets of perfect gravitational balance exist throughout our solar system. Known as Lagrange points, they are positions where the combined pull of two large bodies, like the Earth and the Sun, creates a stable pocket. Here, the gravitational forces and the orbital motion perfectly cancel each other out, allowing a smaller object to essentially park itself, orbiting in lockstep with the planet. The mathematician Joseph Louis Lagrange first theorized these points in the 1770s, long before we had the technology to find objects occupying them. Yet the real mystery is not their existence but what we find there. At Jupiter's Lagrange points, leading and trailing the giant planet in its orbit, we find vast swarms of ancient asteroids known as Trojans. These are not scattered randomly, they are clustered in these stable zones by the millions. Their persistence is what defies expectation. Our models of solar system evolution, which account for gravitational nudges and cosmic collisions, predict that such clusters should have been dispersed over billions of years. The gentle but persistent tugs from other planets, especially Saturn, should have gradually destabilized these swarms, scattering the Trojans to the solar winds. Yet they remain, a fossilized record of the early solar system held in gravitational stasis. This reveals a deeper truth about our cosmos. Gravity, the force of attraction we often associate with chaos and collapse, can also carve out exquisite pockets of order. It creates these celestial parking lots where matter can gather and be preserved against the relentless tide of time. The coincidence lies in their perfect stability, a fine-tuned balance that has protected these primordial rocks for eons. It forces us to question if such stable points are common around other stars, and whether they might serve as way stations or archives in other planetary systems. This gravitational architecture hints at a universe with a hidden preference for order, a theme that becomes even more apparent when we consider the timing of events on a far grander scale. This same rhythm of celestial precision echoes in one of humanity's oldest astronomical discoveries. The Saros cycle is a cosmic clock that ticks with unerring accuracy, bringing a nearly identical pattern of solar and lunar eclipses back to the same location on Earth every 18 years, 10 or 11 days, and 8 hours. This remarkable predictability relies on a perfect synchronicity between three different cycles. It requires the Moon to return to the same phase, to be at the same point in its elliptical orbit around Earth, and for Earth itself to be at the same point in its orbit around the Sun. The fact that these three independent periods align so perfectly over and over for thousands of years feels less like a happy accident and more like a piece of cosmic engineering. Ancient cultures from Babylon to China built their calendars and their mythologies around this cycle, using its reliable return to predict celestial events with a sophistication that still commands respect. They saw it as evidence of divine order. Modern science, of course, explains the mechanics. we know it is a product of orbital resonances, the same kind of gravitational lockstep we see with Jupiter's moons. Experts like Eclipse historian John Steele point to these resonances as the driving force. Yet, this mechanical explanation only pushes the mystery one step deeper. Why do these specific resonances exist in the first place? What initial conditions in the early solar system set these gears in motion with such flawless timing? Our models can describe the clockwork, but they struggle to explain why the clock was wound so perfectly. This synchronicity highlights a universe where profound order underlies the apparent chaos, a rhythm that has guided both science and human culture since the dawn of civilization. It suggests that the cosmos is not just a place of random events, but one of deep, recurring patterns. And as we ponder these ancient rhythms close to home, a far more recent and violent mystery from the outer solar system demands our attention. Far beyond the orbit of Neptune, the solar system does not simply fade into the darkness. Instead, it is encircled by a vast disk of icy worlds known as the Kuiper belt. This distant realm is home to dwarf planets like Pluto, and it should, according to our best models, be a smoothly distributed cloud of frozen debris. But it is not. Astronomers have found that this belt of icy objects does not thin out gradually. It ends abruptly, as if sliced by a cosmic knife. The density of these objects drops off so sharply and unexpectedly that it defies every standard prediction of how planetary systems form. Our leading theory, the nebula hypothesis, describes a gentle process where the outer solar system cooled and condensed from a swirling disk of gas and dust. This process should have left behind a diffuse, fading population of objects, not a wall. The existence of this sharp edge is a coincidence that should not be, a celestial boundary that challenges our fundamental narrative. To explain it, some scientists, like astronomer Konstantin Batygin, have proposed a radical idea. A massive, undiscovered world, a so-called Planet 9, could be orbiting in the blackness far beyond the Kuiper belt. Its gravitational influence would act as a shepherd, carving out this sharp edge by clearing its orbital neighborhood and herding the icy bodies into a confined space. Yet, for all the compelling mathematical evidence, this hypothetical planet remains elusive, its existence unconfirmed by any direct observation. This leaves us with a profound mystery. We are faced with a clear, observed feature of our solar system that our foundational models cannot account for without invoking a ghost, a world we have not yet seen. It suggests that the history of our cosmic neighborhood is far from complete, that there are chapters filled with unknown events or unseen actors still waiting to be read. This strange boundary in the cold dark is a reminder that our maps of the solar system are still being drawn. And as we look from this frozen frontier back toward the warmth of the sun, we find another deep and unexpected connection between our star's behavior and the climate of our world. The sun's own heartbeat seems to echo in the climate of our world. Every 11 years, the number of dark sunspots on its surface rises and falls in a cycle that has repeated for centuries. Yet this rhythm is not isolated in space. It leaves its fingerprint on Earth, correlating with periods of unusual cold and warmth throughout our history. The most famous example is the Maunder minimum, a 70-year period starting in the mid-1600s when sunspots virtually vanished. This coincided with the deepest chill of the Little Ice Age, when frost fairs were held on the frozen River Thames and glaciers advanced across continents. The correlation is too strong to ignore, but the causal chain remains one of science's great puzzles. Solar physicist Joanna Haigh and others have shown that when the sun is more active, its total energy output increases by only about 1/10 of 1%. This tiny variation seems far too small to account for the dramatic shifts in global climate we see in the historical record. Some theories suggest that the Sun's influence might be amplified through complex interactions in Earth's upper atmosphere, perhaps by altering cloud formation or shifting wind patterns. But our climate models struggle to replicate this subtle yet powerful link. The coincidence lies in this persistent, inexplicable alignment. Why should an 11-year cycle of magnetic storms on our star so closely match periods of drought and rainfall, of heat and cold on our planet? It blurs the boundary between astrophysics and Earth science, suggesting our Sun is not a distant, indifferent light, but an active participant in the delicate balance of our biosphere. This deep connection hints at a solar system where everything is in conversation, from the star's fiery surface to the weather outside your window. That same sense of a deep, mathematical conversation appears in a number so fundamental it seems woven into the fabric of the cosmos itself. That same mathematical conversation reveals itself in one of nature's most celebrated numbers. The golden ratio, approximately 1.618, appears not just in sunflowers and seashells, but in the very orbits of worlds. Consider the dance between our own planet and its fiery neighbor. 8 Earth years are almost exactly equal to 13 Venus years. This 8:13 ratio is a close approximation of the golden ratio, a pattern of near-perfect harmony between two seemingly independent worlds. It is an arrangement that feels aesthetically beautiful, almost musical. Yet, when astronomers look for a physical reason, a gravitational mechanism that would lock these planets into such an elegant rhythm, they find none. The gravitational pull between Earth and Venus is too weak to create this kind of resonance. This leads many scientists to dismiss it as mere numerology, a random pattern that our pattern-seeking brains have latched onto. But then you look elsewhere. The same ratio appears in the spiral arms of galaxies, in the branching of trees, and in the proportions of the human body. Its recurrence is so widespread that it becomes difficult to ignore. This forces a profound philosophical question. Is mathematics simply a human invention, a language we created to describe the world? Or is it something we discovered, a fundamental code woven into the fabric of reality that exists whether we are here to see it or not? The appearance of the golden ratio in the clockwork of the solar system suggests the latter. It hints at a universe with an inherent preference for certain forms of beauty and balance, a cosmos that is not just governed by laws, but also by a deep, underlying symmetry. This elegant orbital relationship makes the next puzzle in our journey all the more jarring, as we confront a celestial event that seems to defy the very laws it helped to establish. A slow celestial wobble etches its rhythm into stone. Earth's axis traces a lazy circle in the sky over 26,000 years, a motion called precession, which gradually shifts the backdrop of stars against which our sun rises. This is a cycle so vast it spans hundreds of human generations, yet somehow the builders of monuments like Stonehenge appear to have known about it. The massive stones of that ancient circle are aligned not just to the summer and winter solstices, but to specific celestial events that only repeat over this grand precessional cycle. The coincidence is staggering. How could a society without written language, using only stone tools, encode an astronomical clock with a 26,000-year tick into their architecture? Archaeoastronomers like Gerald Hawkins have demonstrated these alignments with mathematical certainty, proving the stones function as a sophisticated observatory. Conventional history tells us these were primitive people, yet their stone calendar tracks a motion of the planet that science would not formally understand for millennia. This was not just marking the seasons, it was capturing the slow, cosmic breath of the Earth itself. The precision of these alignments forces a humbling question. Did these ancient cultures possess a deep, intuitive knowledge of the heavens, passed down through oral traditions over countless centuries? Or does their work point to a lost chapter in human history, a forgotten understanding of celestial mechanics that we have only recently rediscovered with our telescopes and computers? This enigma suggests a connection to the cosmos that is far older and more profound than we have ever acknowledged. It is a coincidence that bridges the human and the heavenly, written not on paper, but in standing stones that have waited for thousands of years for us to decipher their message. And just as these earthly stones point to the sky, the very rocks we brought back from the moon point to a violent and improbable origin story for our closest companion. The very rocks beneath our feet hold a secret to the moon's violent birth. When Apollo astronauts brought back samples from the lunar surface, scientists made a startling discovery. The moon's composition is almost identical to that of Earth's own mantle, the rocky layer beneath the crust. It is as if someone scooped out a piece of our planet and flung it into orbit. This finding is the cornerstone of the giant impact theory, which describes a cataclysmic collision between the infant Earth and a Mars-sized object called Theia. The debris from this unimaginable crash, a ring of molten rock, eventually coalesced to form our moon. Yet for all its explanatory power, this theory rests on a foundation of staggering improbability. The impact had to be a glancing blow, not a direct hit that would have vaporized both worlds. The colliding object had to be just the right size, and it had to strike at just the right angle and speed to spray exactly the right amount of material into a stable orbit. Alter any one of these variables, and you get no moon at all, or a moon that quickly spirals away or crashes back down. Planetary scientist Robin Canup has run countless simulations of this event, and while she can produce a moon, the conditions required are so precise they feel more like a recipe than a random accident. The coincidences compound when you look closer. The moon is curiously dry, lacking the volatile elements like water and zinc that are common on Earth. This suggests the impact was so violent it boiled away these lighter materials, leaving behind a desiccated world. Even more puzzling is the moon's tiny, iron-poor core. If Theia had a large iron core of its own, as most planetary bodies do, where did that iron go? Some models suggest it was absorbed into Earth's core, while others propose a more complex merging process. The fact remains that our moon's specific chemical signature, its size, and its orbit are the products of a cosmic billiard shot of near impossible precision. This single freak event did not just give us a beautiful night light. It delivered the stabilizer that tamed our world's tilt, the regulator that may have guided the evolution of life itself. The coincidence is not merely that we have a moon, but that we have this specific moon, born from a chaos that somehow produced perfect order. And if such a rare event was crucial for our existence, what other improbable accidents might be hidden in the architecture of the cosmos, waiting to be found? Even our sun presents a paradox that defies the simple story of a steadily warming star. In its youth, our sun was significantly dimmer, shining with only about 70% of the energy it radiates today. According to every model of stellar evolution, a weaker sun should have meant a frozen Earth for at least its first 2 billion years. The math is clear and unforgiving. Yet the geological record tells a completely different story. Ancient rocks show clear evidence of liquid water, of riverbeds and oceans, from a time when our planet should have been a global snowball. This is the faint young sun paradox, a contradiction that has puzzled astronomers and climatologists for decades. Carl Sagan famously highlighted this enigma, pointing out that our understanding of stars and our understanding of planetary climate were in direct conflict. How could Earth have been so warm under such a faint sun? The leading theory points to a powerful greenhouse effect, with an atmosphere thick with heat-trapping gases like methane and carbon dioxide. But this solution introduces another layer of coincidence. The greenhouse effect would have had to be strong enough to prevent a global freeze, yet not so powerful that it triggered a runaway greenhouse effect, boiling the oceans away as happened on Venus. It was a planetary tightrope walk sustained for billions of years. Some researchers propose that a younger Earth, with more active volcanism and a different continental arrangement, had a perfect cocktail of feedback loops that naturally regulated the temperature. But our models show that such a balance is incredibly fragile and difficult to maintain. This paradox suggests that the emergence of a habitable world is not a simple matter of orbiting within a star's habitable zone. It requires a series of geological and atmospheric accidents, a cascade of fine-tuning that kept the thermostat set to just the right level against all odds. The faint young sun paradox forces us to confront an unsettling idea. A life-friendly climate might not be a common, stable outcome, but a rare and fleeting state of grace in a universe of extremes. This delicate dance between a star and its planet finds a strange mirror in the most counterintuitive realm of physics, where reality itself behaves in ways that seem to defy every classical model. Einstein's spooky action at a distance challenges our most basic understanding of reality. In the strange world of quantum mechanics, two particles can become entangled, linked in such a way that measuring the property of one instantly determines the property of the other, even if they are light years apart. This connection defies the cosmic speed limit set by light and mocks the classical idea of a predictable, local universe. Einstein was deeply troubled by this, believing it pointed to a flaw in quantum theory, yet experiment after experiment has proven entanglement is real. The coincidence that so baffled him is now at the frontier of physics, because this ghostly link between particles appears to be deeply related to the very fabric of spacetime described by his own theory of relativity. Modern theorists are exploring the radical idea that spacetime itself might be stitched together by a vast network of quantum entanglement. Think of it like a cosmic tapestry, where the threads connecting every point are these instantaneous quantum links. This suggests that the rules governing the smallest particles are not separate from the geometry of the cosmos, but are fundamentally intertwined. Theories like string theory and the holographic principle attempt to build a bridge across this chasm, proposing that our three-dimensional reality is a projection from a two-dimensional information field, with entanglement as the glue. Yet a complete picture, a true theory of quantum gravity, remains one of science's greatest unsolved problems. This profound mystery blurs the line between the infinitesimal and the cosmic, hinting at a unified framework where everything is connected in ways we are only beginning to glimpse. It forces us to consider that the universe operates not as separate domains, but as a single, deeply interconnected whole. And as we ponder this invisible web linking all of space, we must also confront a far more tangible force from the cosmos that has repeatedly shaped the story of life itself. This same unpredictable force from the cosmos has literally reshaped life on our planet. A 10-mile-wide asteroid striking the Earth 66 million years ago did not just end the reign of the dinosaurs, it cleared the stage for a new evolutionary act. From the ashes of that catastrophe, small, shrew-like mammals emerged from the shadows, seizing an opportunity to diversify into the incredible array of creatures we see today, including ourselves. The coincidence is not the impact itself, but its timing with a major transition in life's history. The fossil record reveals several of these mass extinction events, and a surprising number align with evidence of asteroid or comet impacts. It is as if the universe itself periodically presses a reset button, wiping the slate clean for a new experiment in biology. Paleontologists like Stephen Jay Gould argued passionately that evolution is not a steady, predictable climb toward complexity. It is a contingent process, a story full of accidents and lucky breaks. If you replayed the tape of life, he suggested, you would get a radically different outcome every single time. This perspective makes the correlation between cosmic impacts and evolutionary leaps even more profound. Our standard models of orbital dynamics show that asteroid strikes are, for the most part, random events. There is no hidden clockwork in the solar system that schedules these cataclysms to coincide with periods of biological stagnation. Yet the evidence suggests that these random cosmic interventions have been crucial catalysts for change. This forces a humbling realization. The story of human existence is not just written in our genes or our environment, but also in the chaotic motion of rocks hurtling through space. A single impact shifted by just a few minutes could have missed Earth entirely, leaving the dinosaurs to continue their dominion and preventing our mammalian ancestors from ever taking center stage. This cosmic lottery adds a layer of breathtaking unpredictability to the narrative of life, suggesting that biological destiny is intertwined with the violent, random rhythms of the solar system. From this grand, life-altering violence on our own world, we now turn our gaze to the very edges of everything we can see. Our own galaxy is not at rest, but is being pulled through the cosmos by an immense and unseen force. This is the mystery of the Great Attractor, a gravitational anomaly located in the direction of the constellations Centaurus and Norma, toward which our entire Milky Way, along with thousands of other galaxies, is steadily streaming. The sheer scale of this motion defies simple explanation. The visible matter we can detect in that region of space, the galaxies, the gas, the dust, is nowhere near massive enough to account for the powerful gravitational tug we feel. It is as if we are all sliding down a hill, but when we look for what is pulling us, we see only a faint slope where a massive mountain should be. This cosmic deficit challenges the very foundation of our gravitational models. Astronomers like R. Brent Tully have meticulously mapped this vast river of galaxies, revealing that our motion toward the Great Attractor is just one part of an even larger flow, a cosmic current on an unimaginable scale. The source of this immense pull remains one of the great unsolved puzzles in cosmology. To explain it, scientists are forced to invoke the invisible architecture of dark matter, proposing a concentration of this mysterious substance so vast it can bend the paths of entire galaxies. Others suggest the pull comes from an even larger structure, a supercluster of galaxies whose full extent we are only beginning to map. This enigma forces a humbling realization. The movements we see in the heavens are not just dictated by the stars and galaxies we can photograph, but are choreographed by hidden masses that compose the true, unseen skeleton of the universe. It is a profound reminder that our maps of the cosmos are still woefully incomplete, and that the forces shaping our cosmic journey originate from realms we have only just begun to perceive. This invisible tug on our galaxy finds a strange parallel in the sudden, violent death of stars, events whose timing seems curiously linked to the story of life itself. A dying star can rewrite the history of a world light years away. The violent death of a massive star in a supernova is one of the most energetic events in the universe, and if one occurs too close to Earth, the consequences are apocalyptic. A blast of intense gamma radiation and cosmic rays would strip away our protective ozone layer, bathing the planet in lethal levels of ultraviolet light from the sun. This celestial sterilization event could trigger a mass extinction, wiping out countless species in a geological instant. The profound coincidence lies in the geological record itself. Around 450 million years ago, during the late Ordovician period, one of the 5 great mass extinctions wiped out over 80% of all marine species. Scientists analyzing rock layers from that time have found isotopes like iron-60, a radioactive element that is not produced on Earth. Its presence is a telltale signature, a smoking gun pointing to a nearby supernova that showered our planet with its debris. The timing is uncanny. A stellar catastrophe in our galactic neighborhood appears to align perfectly with a biological catastrophe on our world. Astrophysicists like Neil Gehrels at NASA model these cosmic threats, calculating the kill zone of a supernova to be roughly 50 light-years. Within that bubble of danger, the odds of a planet like Earth being hit by such an event at any given time are incredibly low, yet the evidence suggests it has happened. This forces a startling realization. The evolution of life on our planet has not been shaped solely by terrestrial forces or random asteroid strikes. It has also been nudged by the explosive deaths of distant suns, a cosmic lottery where the fallout from a stellar collapse can determine which species thrive and which vanish forever. The rarity of such a close supernova, combined with its apparent impact on our deep past, weaves a fragile thread between stellar astronomy and paleontology. It suggests that our place in the galaxy is not just a location, but a moment in a much larger, more violent story. Our continued existence may depend on the quiet stability of our stellar neighbors, a stability that is not guaranteed. This invisible connection to the lives and deaths of stars leads us to consider another, more visible and equally mysterious feature of our solar system, the stunning rings of Saturn. Saturn's rings are a masterpiece of celestial engineering, an intricate disk of ice and rock that gleams with impossible perfection. Their delicate structure is sculpted by the gravitational whispers of Saturn's many moons. The small moon Mimas, for example, orbits in a precise 2-to-1 resonance with the Cassini division, the most prominent dark gap in the rings. For every 2 orbits that a ring particle would take in that region, Mimas completes one, and its repeated gravitational tugs act like a cosmic broom, clearing out the area and carving a clean, sharp edge. This is not a simple, chaotic scattering. It is a form of gravitational music, where the rhythms of the moons impose order on the orbiting debris, creating patterns of stunning clarity and beauty. The profound coincidence here is one of timing and stability. Ring systems are not permanent. They are transient cosmic phenomena, thought to last only a few 100 million years at most. The particles constantly collide, grind each other down, and spiral inward toward the planet. Yet, the resonances that maintain their complex architecture, the very forces that prevent the rings from simply smearing into a featureless haze, have remained locked in place for ages. Planetary scientist Carolyn Porco, who led the imaging team for the Cassini mission, has described these rings as both an evolving system and a work of art. How can such fleeting structures exhibit such enduring, fine-tuned gravitational partnerships? Our models suggest that these delicate balances should be easily disrupted, yet they persist. This presents a quiet contradiction, a temporary beauty of staggering complexity existing in a universe of entropic decay. It challenges our sense of cosmic permanence, reminding us that some of the most breathtaking sights in the heavens are also the most ephemeral, their existence a fragile dance between creation and dissolution. This brings us to the final entry on our list, a coincidence that strikes at the very heart of our cosmic address and the fundamental nature of reality itself. Our most precise measurement of the cosmos contains a stubborn contradiction at its core. the Hubble constant, the number that tells us how fast the universe is expanding, should be a single, universal truth. Yet when we measure it using different cosmic rulers, we get two different answers. One method, looking at the ancient light from the Big Bang, gives us one value. Another, using the predictable brightness of exploding stars in nearby galaxies, gives us a slightly faster, younger value. This is not a small rounding error. It is a persistent and growing tension that has defied resolution for years. Cosmologists like Wendy Friedman have dedicated their careers to refining these measurements, searching for a hidden flaw in our instruments or our methods. So far, none has been found. This discrepancy coincides with other fundamental uncertainties about the universe's true age and the precise recipe of dark matter and dark energy that fills it. Our entire standard model of cosmology, known as lambda CDM, rests on the assumption that the Hubble constant is a fixed number. This coincidental conflict, this data that refuses to agree, suggests that our model is incomplete. It could be pointing toward new, undiscovered physics, perhaps a form of dark energy that changes over time, or new types of neutrinos that we have not yet accounted for. This final coincidence is perhaps the most humbling of all. It tells us that after 25 other mysteries that challenge our understanding of the solar system and our galaxy, we now face a fundamental disagreement about the nature of the entire cosmos. It underscores that even our most advanced and successful theories have limits. They are maps, and like all maps, they simplify a reality that is far more complex and mysterious than we ever imagined. These 26 celestial coincidences, from the moon's perfect fit to the universe's conflicting expansion rate, collectively paint a startling picture. They suggest that our reality is not a random accident, but a place of profound and curious order. Each mystery on its own could be dismissed as a statistical fluke. But together they form a pattern, a chorus of whispers from the cosmos hinting that there is far more to the story than we currently understand. They invite us not to a conclusion, but to a beginning, a new era of exploration where the greatest discoveries likely lie just beyond the edge of our current knowledge. Together, these 26 puzzles form a single, breathtaking mosaic. Each one is a crack in the facade of our current scientific understanding, revealing glimpses of a deeper reality just beyond our grasp. The perfect ratios in our solar system, the finely tuned constants of physics, the synchronized dances of distant worlds, they all point toward gaps in our models. Our theories of planetary formation cannot fully explain the resonant architecture we observe. Our standard cosmology runs aground on the precise value of the cosmological constant. These are not failures of science, but rather its essential fuel. Throughout history, the greatest leaps in human knowledge have sprung from exactly this kind of stubborn, unexplained data. Kepler's laws of planetary motion emerged from his struggle to make sense of the messy orbital data left by Tycho Brahe. The bizarre rules of quantum mechanics were forced upon us by experimental results that classical physics could not digest. In every case, the universe presented a paradox that refused to be ignored, compelling a revolution in thought. The collective weight of these 26 coincidences suggests we are living through a similar moment right now. They hint at operating principles we have not yet discovered, whether that be a landscape of multiverses, a deeper layer of fine-tuning, or even the influence of hidden dimensions. They invite us to remain humble and endlessly curious, to see these mysteries not as dead ends, but as signposts pointing toward the next great frontier of discovery. The cosmos is whispering to us, and its message is clear: there is so much more to learn. Our journey through these 26 celestial puzzles reveals a universe far more intricate than any single theory can contain. From the moon's impossible fit over the sun to the conflicting heartbeat of cosmic expansion, each mystery stands as a testament to the limits of our current maps. They remind us that the cosmos is not a solved equation, but a living, breathing enigma, brimming with both profound order and tantalizing secrets. Carl Sagan's words ring truer than ever, that somewhere, something incredible is waiting to be known. These coincidences are the very beacons lighting that path of discovery. I would love to hear which of these cosmic riddles captured your imagination the most. Share your thoughts in the comments below, and if you are eager for more journeys to the edge of understanding, be sure to subscribe. Thank you for sharing this adventure among the stars. Keep your eyes on the sky and never let go of that sense of wonder for the secrets it's